There we are. Now we're being recorded. Eric Carson is a research geologist with the Wisconsin Geologic and Natural History Survey and is currently serving as interim director of the state geologist there. He received his BS in geology from Western Virginia University and both his MS and his PhD, double major, wow, geology and geophysics or geography from the University of Wisconsin-Madison. He has 20 years experience in academia and research. His research at the WGNHS investigates the timing of the last glaciation in Wisconsin, process associated with rivers, flooding, and how landscapes evolve over timescales ranging from thousands of years to tens of millions of years. All right, I think we can go ahead and welcome Eric.
I don't know if Randy saw it, but Eric got kicked out and he has to be promoted to moderator or whatever that is.
Oh, okay. Yeah, it'll take just a minute here.
Okay.
I missed that.
Okay, so
Oh,
I'm going to stop
okay.
sharing my screen if I can do this.
Oh, mistake. I promoted somebody else. I wonder who I promoted. Oh, yeah, okay.
All right, I'm now here.
All right, Eric. I'm
Okay,
trying to close my screen here.
My university computer decided it was a great time to update Zoom clients.
You need to stop sharing, Roger.
That's what I'm trying to do. It's not letting me. Oh, there it is. Stop sharing. All right. All right, everybody. Eric is now up.
All right. Well, thank you all for showing up virtually this evening. Thanks for your interest in the material and in the talk. And yeah, I hope we have a good talk this evening. I have done this sometimes online. I'm used to doing it in person. I often tell people that I apparently must love the sound of my voice because I have a tendency to drone on and on. So I hope that doesn't happen. I'll try to keep on time for you all this evening. And yeah, the moderators can keep track of any questions that might need answered in the flow of the talk rather than at the end. And otherwise, we'll just get going with this. So I am here to talk to you about how rivers have changed in North America over the past 3, 4, 5 million years. And we're talking the central part of North America, what today we think of as the Mississippi River system. This is research that I've been conducting at the Wisconsin Geological and Natural History Survey as part of goes hand in hand with my geologic mapping program. So we use the research and the mapping sort of synergistically, one feeds off the other. Good research questions lead to better maps and better maps lead to good research questions. My background is as a geomorphologist, more specifically a fluvial geomorphologist. So I'm interested in river systems. And I was actually hired at the WGNHS to work in the driftless area of Southwest Wisconsin, the portion of the state that was never covered by any of the cycles of glaciations over the last 2.5 million years. And so this gorgeous picture from sunrise at Ferry Bluff State Natural Area, just outside of Sauk City, Wisconsin, is a view looking west along the lower Wisconsin River into the driftless area. And much to the chagrin of all you Vikings fans and Gopher fans out there, this talk is largely going to start in Wisconsin. That's where we're going to get going. I would like to acknowledge some of the colleagues that have worked hand in hand with me on this project. This is not work that I've done by myself. So J. Elmo Rawling is another geologist at the Geological Survey. Ben Bates was a geoscience technician with us for several years while this work was being done. And John Addig is now a retired geologist from the survey. All right, so let's look at the upper Midwest. Let's look at the effect of the cycles of glaciers that have happened over the past 2.5 million years. So, we as geologists know that having glacial ice on the landscape is actually atypical over the course of the entire Earth's history. But over the last 2.5 million years, we've been in a global setup where ice caps and ice sheets have episodically and periodically expanded and contracted over time. There have been several dozen of these cycles of glaciations, and this map here is showing the end result of all of them that we see in the upper Midwest. So in the old school traditional way of looking at glacial deposits, these get divided into 3 different ages of deposits. So in the gray are what we refer to as pre-Illinoian glacial deposits. Those are all the deposits that are between, we'll say, 500,000 and 2.5 million years in age. And they're so old that it's very, very difficult, certainly out on the landscape, to distinguish different glacial episodes from one another. Younger than all of those combined glacial deposits there are the areas in gold, which has historically been referred to as the Illinoisan glaciation. So that's the penultimate or second most recent glacial cycle that we have evidence for in North America, and it hit its peak in the range of 130,000 to 300,000 years ago. And then finally, most recently in the dark green, we have the Wisconsin glacial episode. So that hit its peak in the range of about 25 to 30,000 years ago. You can see that it covers the largest area on the map, largely because it's just overrun older deposits. And then obviously the one thing that stands out in this view as we look at it is the big white bullseye in the center of the map. That is the driftless area. That's the portion of the upper Midwest that was surrounded by ice at different times on all sides, but was never, to the best of our knowledge, ever overrun by glacial ice. And so what we have is, rather than a landscape that might be 30,000 years old or a landscape that might be 150,000 years old, when we get into the driftless area, we're looking at a landscape that has been evolving and developing for 3, 4, 5, 10 million years. And so we have a window into a much deeper view of geologic time and geologic processes that have been going on in the Midwest. And so this is where we're going to start this talk. Eventually it'll expand out, and it'll touch on all of the Midwest and a huge portion of the mid-continent. But we're going to start right here in this place where we have a good view of deep time in the landscape. Okay, so if we switch over to a landscape view of Wisconsin, if you're familiar at all with the driftless area, you know where it is. If you're familiar at all with looking at landscapes, it should stick out to you. So I'll be using the cursor here. Hopefully you all can see that. So this area is the driftless area here in southwest Wisconsin. And what stands out about the topography is that you're seeing nearly flat-lying Paleozoic bedrock, sedimentary rocks, sandstones, dolomites, some shales that have been incised deeply by streams over time. So you're seeing a nice dendritic stream pattern that's been carved into these valleys, carved into this bedrock to form these valleys. We are going to start by zooming in right here on this red box. This is what we call the lower Wisconsin River Valley. So the Wisconsin River itself starts way up here on the border with Michigan at the UP at Lac Vieux Desert, and it flows south all the way across the state, down across this broad, flat sand plain that was Glacial Lake, Wisconsin during the last glacial cycle. The river loops around the east end of the Baraboo Hills here, and then it flows west across the driftless area to where it joins the Mississippi River near Prairie du Chien, Wisconsin. So that's what we're going to zoom in on. And we're going to zoom into this, and we've switched over to this grayscale view. And this is a topographic modeling system that we use with our research today. If you're not familiar with it, this is called LIDAR. This is called, it's light detection and ranging. So it's a laser system for interrogating the Earth's surface to get topographic information. It creates digital elevation models, and from those digital elevation models, we create these shaded relief models. Now, these shaded relief maps can get very, very detailed. This is a coarse grid of one because it's a statewide map. You'll see ones that are much finer later on in the talk, and the resolution of these things, again, if you're not familiar with these, the resolution of these is astounding. just amazing when you zoom in, the amount of detail you can pick up, the amount of accuracy that you have. I often tell people that when we're looking at these LiDAR maps in our computer systems and our geographic information systems on screen, we can zoom in on agricultural fields, and these LiDAR maps are so detailed that you can tell whether an agricultural field was plowed or fallow on the day that they shot the lasers over the landscape with flights of light airplanes. So that it's really revolutionized the way we look at the landscape, and it's actually one of the bases of being able to do this work. The questions that I've been asking are questions that have been around for decades, but having this technology was one of the key components to be able to answer these questions. Okay, so as we look at this, we see the lower Wisconsin River cutting east to west across the screen. We see the Mississippi River over on the west edge of the screen, flowing south down towards the Gulf of Mexico. Both of them stand out as these big, wide floodplain systems, or lock and dam systems, step pool systems on the Mississippi these days. In both cases, what we're looking at are river valleys that are incised very deeply into the bedrock system. And then there is, in most cases along these reaches of the Wisconsin and Mississippi River, you're talking somewhere in the range of 100 to 150 feet of sand and gravel that's infilling the valley itself, which gives us this big broad surface that we see in the LiDAR. And of course, it makes for a setup where there's a significant discrepancy between the ground surface and the bedrock floor of the valleys, because there is this 100 or 150 feet of sand and gravel filled in there. Now, when we look at this image, and when we look along the lower Wisconsin River Valley, there is one feature that does kind of stand out to a geomorphologist's eye, and I'm going to pop on some boxes to show them. So it's these areas right there. These are three different stretches of a terrace, and it looks like four. We're going to call this one right here one. It's a single one that's bisected by the mouth of the Kickapoo River there. So for any of you, if you're very, very familiar with the geography of the lower Wisconsin River Valley in Wisconsin, this one to the east is right near the town of Muscadet. This one right here that's bisected by the mouth of the Kickapoo River is right near the town of Wazeeka. And this one is right near the town of Prairie du Chien, or Bridgeport is a small town that's right on that one. So we'll pull it away, and there you can still see it. You see that it pokes out pretty broadly to you. You can look at the scale, you can see that, we're seeing 70, 80 kilometers east to west across this map. Some of these are still standing out pretty clearly, some of these terraces. So let's talk about stream terraces, because these pieces of stream terrace that I just highlighted are very, very interesting to us. Okay, so terraces broadly can get divided into two different categories. They represent the same thing. They represent a former floodplain surface. So they're flat surfaces that are at some elevation higher than the modern floodplain, than the modern river surface, and they represent times when the river was flowing at that higher elevation. The two that we have, there's a different sequence of events that go into forming them. And what's significant about them isn't the surface of them, because the surface is always going to be a relatively flat surface, something above the floodplain. But the big thing is going to be the material that makes it up. One end of the scale, we can talk about what we call fill terraces often, or depositional terraces. And so those are terraces that the material that makes the terrace is unconsolidated sediment. It's often sand and gravel. And so you can see on this image on the top left, we've got terrace 1 that was an original floodplain surface. We've got terrace 2 that was a lower and therefore younger floodplain surface, and then the modern floodplain. But to get this terrace, you have to have actually a 3-step sequence. You have to have the river cut down to form the bedrock floor of the valley. And then you have to have the valley fill up all the way to this terrace 1 level with sand and gravel, or even higher. And then you have to have episodic down cutting to get to the modern floodplain. So there's that 3-step system of cutting, filling with sand and gravel, and then cutting into the sand and gravel. this kind of terrace is literally a dime a dozen across the Midwest. We see these terraces everywhere. We see them on the Mississippi River. We see them on the lower Wisconsin River. We see them on all the tributaries to these rivers. And the reason for this is this kind of terrace can be formed very efficiently by the start and end of a glacial cycle. If you have a glacial cycle start and a glacier advances into the Wisconsin River Valley or the Mississippi River Valley, it's going to be pumping out billions of tons of sand and gravel from the margin of the glacier. And that sand and gravel will be what fills up the valley. That's what we see in the LiDAR on the Mississippi and Wisconsin rivers. And then once the cycle of glaciers end and the source of the sand and gravel goes away, then the river can start cutting back down into the sand and gravel that filled up the valley. So that's why we see these sand and gravel terraces just everywhere. Other end of the scale, we have this terrace that's called a strath terrace or an erosional terrace. This is a terrace that is formed by a simpler model. There's only basically one event that's going on. You have the terrace, and then you get down cutting to a new level, then you get a down cutting to another new level. And because it's just that simple one step of cutting, the material that forms the terrace right here, if we look into the earth, what's forming this terrace too right here, it isn't sand and gravel. It may have a thin skin of sediment on top, a few meters or even a few tens of meters, but the terrace itself is formed by bedrock. And so it's a very different material, obviously, but it tells of a very different geologic past. And this is a type of terrace that we don't see very often in the Midwest. And the reason we don't see it is because the Midwest is tectonically stable. A lot of times the most obvious method for forming these strath terraces is bedrock uplift, mountain building events. So if you go out to the Colorado Rockies, you see strath terraces everywhere. Here in the Midwest, we don't see them. What we see in the lower Wisconsin is this. So we see that terrace that I pointed out up here at a highest elevation, and that's called the Bridgeport Terrace. It's been named. And then we see a series of fill terraces down lower. So we get elements of both kinds of terraces. And this is our question. You know, we look at the landscape, we're like, what's going on? Why is this strath terrace here? What does it tell us about the past? You know, the other thing, like I said, these terraces, the higher they are, the older they are. So this Bridgeport strath is far and away the highest terrace in the lower Wisconsin River. So it's telling us about the oldest geologic history that we're going to be seeing here. All right, so let's go back to this look and take a closer look at these three stretches of terrace. So at the top is that stretch at the eastern end near the town of Muscadet. At the bottom right is the middle stretch that's been bisected by the Kickapoo River near Wazeeka, and at the bottom left is the segment near Prairie du Chien. And so this is getting into some of the higher resolution topographic data that we've got, the higher resolution LiDAR that we've got, so we can see more and more detail. If we were to zoom in on these, we could see even more. And so as we look at this, we'll look at this one up near Muscadet. So this is the southern edge of that bedrock strath terrace right along here. And then as you get down a little bit farther south, this is the floodplain and the fill terraces, sand and gravel terraces along the lower Wisconsin River. And you can actually see really nicely here, you can see the scarp at the edge of the Bridgeport strath terrace there. Then you can see the scarp at the edge of a fill terrace there. And then you can see another scarp at the edge of a lower fill terrace there. So we can see numerous of these sand and gravel fill terraces. We do know that we can confirm just by visual observation that the Bridgeport Terrace is a strath terrace. So these 5 places that I've just identified in red circles are places where you can actually see the bedrock core of the terrace. There's been incision or cutting in some fashion that you can actually see that there's bedrock forming this well up above the level of the modern lower Wisconsin River. If you look at those 2 blue arrows that just popped up, you can see that they're pointing to little scars and cuts on the landscape. Well, that's getting down onto the sand and gravel terraces. And what you're seeing there in the LiDAR is those are sand and gravel quarries. You're actually able to see these quarries. And again, if you could zoom in, you'd be able to see, you know, the shape of the quarry. You'd be able to see sand and gravel piles in the quarry. Really obvious what's going on. And so where these quarries are sitting, it may be as much as 100 or 150 feet to get down to bedrock. Whereas right over here, bedrock is above the river level when you're up on this Bridgeport Strath Terrace. Just to give you a view of them, this is that biggest one, the eastern one near Muscadet. So we're looking to the due west. So we're looking parallel to the Wisconsin River in this view. So the Wisconsin River is off behind this screen of trees. You're able to look down this valley, I think it's about 15 kilometers to the other end of the Strath Terrace. So billowing high surface. In this area, you have to go down maybe 10 or 12 meters to get to the bedrock surface, but you're also still 20 or 25 meters above the floodplain. So, you know, we really do get a sense that this is a Strath Terrace. If we go down a little bit farther, now what we're doing is we're looking south off the same terrace. So we're looking directly at the Wisconsin River. So again, there's this screen of trees here, and the Wisconsin River is flowing left to right behind them. And you can see the drop on this gravel road. This is dropping from the Bridgeport Terrace where we're standing down onto one of the sand and gravel terraces down lower. And then over here on the right, you can actually see one of those two sand and gravel quarries that I pointed out on the LiDAR earlier. Now, this is a drop of at least 20 meters to get from up here down to there. And when we put in a core here, we found that at this location, it was just over 4 meters to get down to the bedrock surface. So again, just reinforcing that this is a bedrock terrace. Okay, so let's take a cross-sectional view of this. So let's draw in a cross-section line here along the lower Wisconsin River and take a vertical slice into the ground and see what this Strath Terrace and these cut and fill terraces mean along the length of the lower Wisconsin River. Okay, so here's a diagram. This was from a publication that Jim Knox and John Addig had in 1988 in the Journal of Geology. Basically, I'm going to be refuting what the two of them said in this journal article. That's not a bad thing. That's the way that science works. And it also so happens that John Addig is one of the people that I identified at the beginning of the map, at the beginning of the talk, as a collaborator. And Jim Knox was my PhD advisor in geography. So both of them were very much on board with this work. There's a lot going on here, so let's step through it piece by piece. So down here at the bottom, we have the solid black line. That is the bedrock floor of the Wisconsin River. And then you've got some distance up until you get to the modern floodplain, until you get to the ground surface. So this is between the black line and the green line. That's the fill of sand and gravel that's happened in the lower Wisconsin River Valley. The green dashed lines are 3 of the most prominent cut and fill terraces that occur. And you notice on all of these, we've got east over here on the right of the image and west on the left. You can see that all of these surfaces dip from east to west. And so these are all surfaces that were either carved or deposited by rivers. They are by the necessity of gravity. They're going to be dipping in the direction that the water was flowing. So the very fact that the bedrock floor of the river valley, the ground surface, and these cut and fill terraces all dip from east to west tells us that they were all carved or deposited by water flowing to the west. When we get to the upper right-hand corner of this schematic diagram, that's where things get a little bit messy. And this is their representation of this Bridgeport Strath Terrace. So what they've got in here is the ground surface, sort of cartoonishly drawn in as the blue line. They've got this surface here which is the top of a package of sediment, and then down here they've got the bedrock surface, the surface of this bedrock strath. Now they've made a couple of interesting observations, and they've made one very critical sort of punt. And the critical punt that they made was that they've drawn this as basically flat. And I just said these things need to be dipping in the direction that the water flows. The reason they did this is they didn't have enough information to be able to tell which way the Bridgeport Strath dipped. They knew that it had to dip either to the east or the west. They only had a couple places where they could see the bedrock in road cuts and the like, and with streams that dip on the order of a few centimeters, streams that slope on the order of a few centimeters per kilometer, there was no way they could figure out which way it dipped. And so they just drew it in as basically a horizontal line. Now, the important observation that they made, the really important observation that they made, was this triangular package of sediment that's listed here as being Bridgeport outwash. So this outwash was sand and gravel that was being deposited coming from the margin of a glacier. And very importantly, they recognized in it that it had cross bedding that indicated that it was deposited by a river flowing to the east, flowing in the opposite direction of the modern Wisconsin River. Now, if we flick back to a map really quick, what they were depicting and what they were understanding was that there was a margin of a glacier shown here by the dashed red line. And that is the eastern edge of that ice. So that ice was flowing to the southeast out of Minnesota and Iowa. Now, what Knox and Attic presumed, they presumed that the pattern of rivers we see today represents the pattern of rivers that existed going back prior to the Quaternary glaciations. And so the conclusion they made in their work is the fact that there were outwash deposits associated with this glacial margin that were flowing to the east. They interpreted that to say that this glacier must have come and blocked off the mouth of the lower Wisconsin River Valley and temporarily caused the water to flow the opposite direction. But then the glacier would have retreated and the river would have resumed its normal course. But if we go back to that, there's actually another option. And the other option is the rivers weren't organized the way they were today. You know, we could have had a radically different system of rivers on the landscape. And the way to test it would be to figure out which way this bedrock surface dipped. If it dips to the west, like all of these other surfaces, then it would tell us that they were right, that it was just a temporary blockage of the Wisconsin River. But if it dips to the east in the opposite direction, then we've got to start thinking about a wholesale reorganization of rivers in the mid-continent of North America. And this is what we set out to start looking at, my colleagues and I, going on, holy cow, it must be 8 years ago we started doing this, the field work for this research. Okay, so like I said earlier, the catalyst for us being able to really address this was the advent of LiDAR data. So what I'm going to do is show you a few images. So obviously, and these three images will be of the exact same area. This is right down near the mouth of the Wisconsin River, almost where it meets the Mississippi River. So obviously, most of you are familiar with this view. This is a topographic map. So this used to be our baseline data for topographic information. Great for showing general patterns, but if you're trying to find the elevation of a single location, you're going to have an error in the range of feet to maybe tens of feet, depending on how extreme the topography is. Going on about 20 years back, we started getting this LiDAR data. So this is a low resolution LiDAR image, statewide LiDAR image for that exact same area. So you're seeing the same pattern of rivers and such. And then starting about 10 years ago, we started getting in this higher resolution data. Now, the lower resolution data, you can see down here that I said it's got a 10-meter resolution. What that's meaning is that they divided the Earth's surface up into 10-meter squares and assign a value for the elevation of that 10-meter square. For this new data that we've got, it's got a 1.5-meter resolution. So obviously the squares are much smaller. which means that each one is going to be much, much more accurate. And because they're so much smaller, you start seeing a lot more data showing up. You can see pretty clearly, you can see here is a road cut on Highway 60 right here where they're cutting through the bedrock, and a road cut right here where they're cutting through bedrock. You can see places here where they had to put in fill. You can see the patterns of streams, and you can see gullying, and you can see this is, I think this is associated with a country club. If you zoom in on a lot of these, you can see the footprints of houses on the landscape. There's even some places where you can zoom in and see individual gravestones and cemeteries on these things. The quality of the data is incredible, and truly this image doesn't even do justice to it until you see it in a GIS environment and can zoom in and see the level of detail. I've had the GIS technicians that we work with that work in our office to support our work run some tests, and they tell me that unless you're on a place where the land is extremely steeply sloping, like here where you've got these steep scarps, if you're up on some place like this and you click on an individual grid square and the machine tells you what the elevation is, it's going to be accurate probably to within about 2 to 3 centimeters plus or minus. So the level of detail, think of going back to the topographic map where we're talking in feet or maybe tens of feet of error to a few centimeters of error, is, you know, it's transformational having this level of data. I'll go back to this for a second. What this let us do was it let us pick points on the Earth's surface and know the elevation to a degree we'd never known before. And this is really key for us for figuring out what the elevation of that bedrock surface is that's buried. The other key component is a methodology that I brought with me when I came to the Geologic survey. I was the first one at our survey who started using this, and this is a coring methodology called geoprobe coring. And so this is a geoprobe setup here, and the way geoprobe works is they take a hollow steel tube and they use simple hydraulic percussion and drive it down into the ground. And then they drive it down in 5-foot increments. So I apologize, being a scientist, I'm going to have to jump back and forth between English and metric units as I do this, because they always think in 5 feet increments. So they'll hammer down 5 feet, pull it back, and we get 5 feet of sediment. And then they keep doing that down the same hole, and they can go down. Typically we shoot to go down until we hit the bedrock surface, and then percussive hammering doesn't let us go any much further. Or there are some places where it's too deep for us to get to bedrock with this coring method. And our deepest cores that we've put in have been in the range of 85 to 90 feet in some old lake basins. But here we're going to certainly be hitting the bedrock surface before we get that deep. So we'll have a nice LiDAR image that tells us what the elevation is right where we park that truck. We'll have nice cores that can tell us how deep we went because we're going down 5 feet at a time. And then if we can identify exactly the depth at which we actually hit bedrock, then in a single place, we can actually pinpoint the elevation of that buried bedrock surface. Now, this really is a profound change for our survey, being able to use this geoprobe coring almost as profound as the LiDAR data. To give you a sense of it, you know, it's a wonderful system for us. It's very quick. We can usually collect in a good day, we can collect 200 to 250 feet of core in a day. It's quick, so we can get that much core done, which is great if we're doing a lot of cores that are in the 20 to 25 foot range. I mean, that means we're getting 8 or 10 or 12 cores done in a single day. It's inexpensive by the methods of geologic coring. It costs us all in. It costs us about $9 a linear foot to collect it. That compares to the bedrock geologists we have, who, when they're going out to collecting bedrock core, these days it's usually about $140 per linear foot. So it's a real bargain. And then the other nice thing is we can set it up on any highway shoulder like this, any rural road shoulder like this. You know, the realities of modern life as people are more and more suspicious about letting you on the land. We could chew up entire days trying to get landowner permission. But with this geoprobe where we can just park on the shoulder of the road and catch our core, we don't need landowner permission for doing that kind of work. So it really checks all the boxes that we would want for a coring methodology. So we're going down, we're trying to identify when we hit the core. And in this project, one of the true things that blessed us was the layer of bedrock that forms the buried bedrock surface. So the layer of bedrock it's a unit known as the Tunnel City group. It's a sandstone, and the characteristic thing about the Tunnel City group is that it has an abundance of glauconite, the mineral glauconite in it, which is a bright green. So bright green is not a color we normally see in unconsolidated sediments near the Earth's surface. So when we hit green, we know we're in the Tunnel City group. And that's in my hand, that's the tip that goes on the first barrel. And it was actually penetrating into the sandstone. And so you can see that that tip there is packed full with this bright Kelly green sandstone. So that's telling us that we were into the sandstone for sure. Okay, if we look at it in a core when we split it, this is what we're going to see. We can see right there is a big whitish gray lump of chert that is sitting right on the contact between this Tunnel City group sandstone below and then unconsolidated recent sediments above that are brownish color. Now I just told you that the Tunnel City sandstone is a bright green, and that you're looking at it, you're like, that's olive green to brown at best. It's weathered. Okay, so that is pretty deeply weathered. It is a weak sandstone. It's poorly lithified. So even with this percussive hammering, in a lot of places, we were able to hammer 3, 4, 5, 6 feet into it before it was solid enough for us to not be able to drill anymore, hammer anymore. And so this is that same core, only a few feet deeper. So there you can see those bright green bands in it. So that tells us that we are in the Tunnel City sandstone. But if we look back at the orange arrow is pointing at the top of the bedrock surface. We can see we can identify that down to the centimeter. So now we not only know the elevation of the landscape to within a few centimeters, we can tell how deep we had to go down to the individual centimeter to hit the bedrock surface. So we can say with confidence at any one point that we want to core, we can say the bedrock surface, even though it's buried, it's at this exact elevation down to within a couple centimeters, which is fairly amazing. If we're looking at this surface that is dipping really, really gently, what we're going to want is a lot of data. So you can see up above each one, it shows how many cores we collected. We basically took a brute force approach and put in as many cores as we possibly could. So here are all the locations that we put in these geoprobe cores. And so for each one of them, we know the exact elevation of the bedrock surface. And now if we plot this up into a cross-sectional view, it should show us which way the bedrock surface was dipping. Was it dipping to the east or is it dipping to the west? And when we plot up the data, this is what we get. So 0 kilometers here. This is the mouth of the Wisconsin River where it meets the Mississippi. This is going, as we go this way, we're going off to the east. We're going up the Wisconsin River. And when you look at this, what we'd expect from this are a high line that we could connect up with a lot of scatter below it. And this is because we'd expect there to be some erosion of that bedrock surface. And lo and behold, this is exactly what we're getting. And if we want to connect up the highest points across here, this is our best bet of what we'd come up with. Now, the Wazeeka segment, all of those were low. We just think there was a lot of erosion there because of the mouth of the Kickapoo River. You know, if you look at just this segment near Muscadet, you really do get a sense of this dipping to the east just from this one segment without the other ones. And then we connect all the way back up here. Now, if any of you have a statistics background, linear regressions, you'd be looking at that and you'd be saying, well, this one data point here at the west end of things is really controlling that gradient a lot. And you know what, we can do that. We can take it away. Even if we take that high point at the west end of things away, you know, we still have something like 6 different core locations here that are all higher than the highest point here. So maybe it affects the slope a little bit. It doesn't affect the conclusion that the surface of this bedrock strath is dipping to the east. So if we put that back up there, the gradient that we get is 0.15 meters per kilometer, which is a pretty reasonable slope for a stream in the mid-continent of North America. So this is starting to make us think that rather than streams looking like they've looked in the pattern that we see today, going back millions and millions of years, it's starting to make us think that we had a radically different organization of streams in the mid-continent of North America before the glaciers came along. And so if we go back to a simplified version of that diagram, this is what we would get. This is the Bridgeport Strath drawn in with that slope that I showed. So you can see that it's pretty similar to the slopes of these other surfaces associated with the modern Wisconsin River. We also get an idea why we don't see, you know, this is that big section of the Bridgeport Terrace near Muscadet. This is why we don't see it going any farther east on the Wisconsin River. You know, it may be up here, but this is dipping down to the east. So if any more pieces of that terrace exist, they're buried underground by these younger terraces from the westward flowing Wisconsin River. Okay, so this is what we see from the rivers today. This is the Wisconsin River flowing west across the driftless area, the Mississippi River flowing east. We are proposing a radically different organization to the streams, and we don't want to hang our hat just on the basis of those cores. So if we're going to come up with a radical claim for what's happened to these rivers, we want some pretty convincing evidence to go along with it. And when we look at the geomorphology of the lower Wisconsin River Valley, we see evidence in a lot of different ways. So the first thing that we'll see are these tributary streams that are all shown up in orange now. And the interesting thing about them is that the lower Wisconsin River flows to the west, but all of those streams join the Wisconsin angling to the east. Now, under most geologic conditions, unless there's some overriding bedrock factor, which doesn't exist here, all of these streams should be angling in the direction that the lower Wisconsin River flows. They should be angling in to the west, but they all angle in towards the east. In the geomorphological literature, going back over 100 years, this situation, these have been called barbed tributaries. And the very presence of just these barbed tributaries is enough to have geomorphologists claim that rivers have reversed their direction over time. We can also look at this edge of the valley wall where the Mississippi and Wisconsin River meet. You can see that it forms a nice, smooth, curved radius here. Well, if you got a valley wall where 2 rivers come together, there's really no good mechanism for making that a nice, smooth, curved radius. You know, rather than looking like the inside of where 2 rivers join, that actually looks a lot more like these spots, where you've just got a tight curve in a river. That's a methodology that can make that nice curve. So that shape itself really doesn't look like it should be there based on the river system that we have today. Now, if we pull these away, what I want you to do is look at the width of the Wisconsin River Valley from valley wall to valley wall. And as we go to the west, and you go progressively farther west, you're going downstream on the river today, the river valley gets narrower and narrower. And that obviously is the direct opposite of what you'd expect from any river. As a river goes downstream, the river itself gets bigger, the valley gets bigger. This is the exact opposite right here. It's getting smaller in the downstream direction. The last one we're going to talk about, the last evidence that something weird is going on in this area is down on the Mississippi River itself. So we'll pull this up. It's showing a little bit farther south. So here we have the lower Wisconsin River joining the Mississippi. And now when we look at this, this almost in and of itself has the appearance of a barbed tributary where the Wisconsin River joins the Mississippi. But what I want you to look at is the Mississippi River Valley itself. And again, look at the width of the river valley. So here we've got this width of river valley from valley wall to valley wall. The river comes down. It's joined by the Wisconsin River, so it becomes significantly larger. But lo and behold, the valley itself gets radically narrower, and there's no bedrock control that would cause that. So why would you have two rivers join and the river gets narrower as a response? Well, again, if you look at the geomorphic literature, geologists would say that this is an indication that this is a very young stretch of stream, that the main stream has had the erosive power to cut down vertically, but there hasn't been very much time for it to cut out laterally and make it wide. And not only do you see that the river valley gets narrower, but the tributaries that are coming in changing character too. You can see that these up here extend all the way back up to the upland surfaces. Whoop. Whereas when you get down here, these tributaries are really short, really steep. And again, it's a sign to geomorphologists that this is a really young stretch of river. Okay, so what are we going to propose? What are we going to say has been going on here prior to the glaciations? Well, this is the lower Wisconsin River, Mississippi River as we see them today. And right here, we have Military Ridge, which is a high bedrock surface. And we are going to propose that prior to the Quaternary glaciations, this area was occupied by a single river that was coming down and flowing to the east. We're going to propose that the lower Wisconsin River Valley was carved by a river flowing to the east rather than to the west. To get away from talking about Mississippi and Wisconsin rivers, to keep these straight, as we go back in time, we're going to start calling this the Wyalusing River, and that's named after the little tiny town of Wyalusing that's right there, and right at the point of land overlooking the confluence of the two rivers is Wyalusing State Park. So we're going to claim that this Wyalusing River existed. It was probably turned to the east by the high bedrock surface of Military Ridge here. I mean, this does tower some 400 feet above modern stream level. It's capped by really resistant dolomites, so just the kind of thing that could convince a river to find an easier path, in this case flowing off to the east. But what happens is we get behind the Wisconsin glacial margin right here, and so we lose the surface expression of what's going on in rivers with the rivers. And what we want to know is, where did this river go after this? Now, if we go up here in Wisconsin, this is the Niagaran Escarpment. So this is the Silurian dolomite that forms the Door County Peninsula. And our question is, does this river continue off to the northeast, or did it find a low spot to drop down to the south and continue on? So the way we went about assessing this, because again, we're going to an area that's been covered by glacial sediment, is we started looking at water well records. And that's what this image is showing you. So it's extending from Sauk and Iowa County right here near the glacial margin, all the way up to, this is Marinette County, Michigan. Now, for all those counties in Wisconsin, the Wisconsin Geological Survey, my office, is the state mandated repository for well drilling records. And on this map, each one of these well records, each one of these red dots represents a well that was drilled, and the data from the logs from drilling it were submitted to our office. In this image, we're seeing something in the range of about 110,000 well records. And I had my geotechnician Ben Bates sort through all these, discard the ones that didn't go to bedrock, so couldn't give us any bedrock information. He had to geolocate them because they only tell depth to bedrock, so we had to know exactly what the ground surface elevation where they were actually drilled was. So he put a lot of legwork into this. But at the end of the day, he was able to produce a map of the buried bedrock surface. And so that's what we're seeing here in this image on the right. The reds are highs, the greens are lows. And so what we're looking for is, was there a way for the water to escape down to the south, or was it going to be funneled continually farther up to the northeast? You know, and when you look at that, the first thing you see is there really isn't any real low spot where the water could get to the south. We do see the evidence of that Niagaran escarpment, that high escarpment of Silurian bedrock. We see evidence of Military Ridge as a bedrock feature continuing in here. So really no place for the water to be routed to the south. What we see are these greens, these deep greens, these lows that continue in this way. And so this would be the course of this river, connecting up all the lows, extending all the way up to the northeast. And this is getting us up to the area of Green Bay. Now we want to know what the slope is. We want to have an idea if it's at the right elevation, right slope to make sense with what we've seen in the driftless area. And so I had our GIS technicians take this green line of where we think the river was and query every well record that was within 500 meters on either side of it. So a kilometer wide corridor of well records. And we're plotting them up in a cross-sectional view, and this is what we get. And that's quite a messy cloud that we get. But we're not really worried about that. That's kind of what we'd expect. We'd expect it for a couple reasons, because we've got this kilometer wide corridor we're collecting. So some of these might be up on valley walls. It's also an area where the bedrock is sandstone. So it's difficult when they're drilling these things to tell the difference between young sand and old sandstone that's chewed up. And even the quality of the well drillers themselves. A lot of them don't have much or any geologic education. So a lot of times they're just making their best guess. So we're not worried about the scatter of these data points. If we connect them up with a solid line, it surely does dip to the northeast. So northeast is up here, southwest is down at this end. So it's giving us an indication of a valley that does dip to the northeast, just like we'd want. And then right in here in this blank spot on the diagram, right in here is where we were doing our coring along the lower Wisconsin River. Now I'm gonna do something. I'm gonna reveal both our core data from the lower Wisconsin River, and I'm going to extend this line. So this is an important thing. The line here, the trend line that I'm going to show, isn't tuned to our coring on the Bridgeport Strath. It's just extending this trend line that we made from the red data points. So we'll extend that up, and when we reveal that, that is what we see. So with the core data from our geoprobe, obviously there's almost no error at all in those, so that they're lined up like soldiers. And if we extend this trend line, it hits them almost exactly. So what we're able to conclude from this is that we are seeing the downstream extension of this Wyalusing River that flowed to the northeast. Okay, so this gets us to a point where we've got a river that flows so far to the northeast that it had to be part of a different drainage system. It couldn't be part of the Mississippi River drainage system. And so what we want to know is, how did this happen? What would we have to have done? And so what we can do is we can look at the LiDAR, and you should recognize this as the lower Wisconsin River and the Mississippi River, but the Mississippi River is missing beyond this. And what I've done is I've just gone into Photoshop and photoshopped the Mississippi River away, because we're going to say this is our Wyalusing River. This is what it would have looked like. And it would have been part of the St. Lawrence drainage system. It would have flowed by the time we finished our work with the well construction records. We'd trace that river all the way up into Green Bay, up into the Lake Michigan lowland, and from there it would have gone out the St. Lawrence drainage into the North Atlantic rather than into the Gulf of Mexico. And so we can envision a time in the past where this is what the river systems would have looked like. We would have had this one Wyalusing River that was flowing in an easterly direction across this image. Here is our military ridge, which would have been the high bedrock surface that convinced it to flow that direction rather than south. And our river would have been flowing something like that. There is our inside of the confluence of the two rivers that looks odd in its configuration today, but wouldn't look odd at all in that configuration. There are the tributaries on the lower Wisconsin River Valley today that they're no longer barbed tributaries. They're angling into the river just like we'd expect. Excuse me. And then down here in what today is the Platte and the Grant and the Turkey rivers in Wisconsin and Iowa, those are what would have been the uppermost end of the Mississippi drainage system back prior to the Quaternary glaciations. Now we'll take some of these away. And during the early part of the Quaternary, there would have been this glaciation coming from the east that was originally identified by Knox and Attig in their paper. So it would have been coming down. Rather than blocking an east flowing river, it just would have been pushing out wash down this, rather than blocking a west flowing river, it just would have been pushing out wash down this river that was here. You know, there would have been times that it would have retreated away. And then later in the Quaternary, rather than ice coming into the region from the northwest, ice began coming in from the northeast, coming from the Hudson Bay lowlands. And it would have eventually gotten to where it would have blocked this river. And when it blocked the river at the downstream end, what it would have done is formed a lake. The lake would have backed up, it would have spilled up, and it would have backed up until it spilled over the very lowest point in the landscape where it could get through. You know, right here, there has to be a lowest point somewhere. Why not here? And once it cuts through there, and once it cuts through the resistant dolomites up at the top of the landscape, then it would be able to reroute itself and become the Mississippi River that we know today. And then eventually the empty Wyalusing River Valley would have been occupied by the modern lower Wisconsin River Valley. This reorganization of rivers would have caused a downcutting of the rivers. There would have been rapid downcutting after this reorganization because the base level change that occurs was shortening the distance to the oceans. So there would have been rapid downcutting on the rivers, which would have left these pieces of the Bridgeport Strath Terrace behind. And it also would have made the accommodation space for all the sand and gravel that fills the Mississippi and Wisconsin rivers today. Now we have the barbed tributaries in there. Okay, so I'm going to try to wrap up here in just a few minutes. So we're going to expand outward again. We're going to look at other regions in the mid-continent and see how this plays out. So here's our little Wyalusing River that we traced this far to where it got into the Lake Michigan lowland. Today, this is the modern continental drainage divide. So this divides water that flows to the south in the Mississippi River drainage system versus water that flows to the east in the St. Lawrence drainage system. And you can see that we've got our river crossing the drainage divide, and rivers can't do that, obviously. So we need to come up with a way to move it. We need to explain this move, which we did locally by moving it to here. But we want other evidence. We love corroborating evidence. And so this is a publication by a fellow named Jim Galloway, who works for the Texas Bureau of Economic Geology. I'm going to run through this in super quick here. Be happy to answer questions about it later, but I don't want to drag this on too long. What Galloway was doing was he had access to seismic data from the oil industries down here in the Gulf of Mexico. And he took all the seismic data and he packaged it out into ages of sediment. And then he looked at how the amount of sediment coming down the different rivers changed over time. and use that to infer changes in drainage basins, the reorganization of rivers over time. So basically, he's using seismic data to get at the reorganization of rivers. In his publication, he made a whole series of these paleogeographic maps that in the dark blue, they show modern rivers. In the teal, they show really cartoon version of ancient rivers. And then the green dashed lines are drainage divides. And so this is his map of Pliocene time right before the Quaternary glaciations. And lo and behold, he puts on a drainage divide within a few line widths of where we would have put it based on our data. So here's Military Ridge. This is what we said the drainage divide would had to be. Galloway would have put it right in the exact same spot based on the amount of sediment delivered down to the Gulf of Mexico. Okay, if we look farther east, if we think about these things in a bigger picture, what we always want to do is go to the geologic literature, and we can see evidence that people found similar identical reversals of other rivers in the mid-continent, and they found them going back over 100 years. So this publication here was published in 1903, I believe, was the publication date for it. And it's looking at drainage modification of the Ohio River. We can look at one that was published this one was published in 1894. And this one that we don't have the further studies of drainage features of the upper Ohio basin. So they were looking at reorganization of the upper end of the Ohio River basin, 1894. They were using a lot of the same techniques, not the coring, but they were using the evidence of barbed tributaries, the evidence of how terraces were dipping in different directions to recognize the same things going on in the Ohio River that we've seen in the Mississippi. And so if we take these away, if we start adding their data into these images, so here's what we're going to add in as our Wyalusing River. We can't just truncate it where we saw it. We figured that parts of the uppermost Mississippi and Minnesota rivers would have had to have been part of it. From the first publication, there is this river system in central Ohio that was a northward flowing river system, the Taze River it was called. From the second publication, what today is the Monongahela and Allegheny rivers were also part of a northward flowing river system. And then we can fold in information that the Ontario Geological Survey has done in the Great Lakes region to piece together prior to the Quaternary glaciations. We would have been looking at a major river system that looked like this. The authors of those two publications that work down here, they found the exact same evidence. They found strong evidence of glaciers that dammed this river. So we wind up with this just wonderful, parsimonious explanation for how all these rivers change. Drainage divide is there, lower Mississippi is there, and at some point we would have had this glacier that came down and blocked all these different parts of these rivers. And so in the east, in Pennsylvania and West Virginia, this river that formed was called the Monongahela River, was called Glacial Lake Monongahela. This one was called Glacial Lake Tite, and this we've called Glacial Lake Muscadet. So there's our three rivers that were dammed up into lakes. All three of them would have been doing the same thing. They would have been filling up until they spilled over at the lowest point and causing reorganization of rivers. And these are the places that these spillovers would have occurred. And at this point, I can never resist doing this. I need to tell people that this is, in ways you could never imagine, this is a map of my life. Because this spillover point on this Glacial Lake Tite, this is right near the town of Madison, Indiana, is where it spilled over. And that's the town that I was born in. The Glacial Lake Monongahela here, where it filled up down into West Virginia. I grew up in northern West Virginia. I went to undergraduate at West Virginia University. the campus of West Virginia University is on the ancient lake bed of Glacial Lake Monongahela, and that's where I first learned of these ancient lakes in my geomorphology classes. And then up here, this is the work that I've been doing in the last 6 or 8 years, working for the Geological Survey on the same kind of thing that's happened. Once these spillovers happened at these points, the water would have been routed down towards the Gulf of Mexico and would have formed the modern river systems that we see today. So we've got in all 4 of these areas, excuse me, all 4 of them are riddled with these barbed tributaries. So it's once again, it's just reinforcing that we're seeing the same thing over and over again in multiple different places. And there's our old drainage divide. The drainage divide was actually moved to the north and the east as a function of the Quaternary glaciations. All right, I appreciate y'all hanging in with me. It looks like I went almost right at an hour. I'll take us back to our beautiful morning view of the lower Wisconsin River Valley. I really do thank you for being here and listening to me tonight, and I'd be really thrilled to answer any questions that people have. Thank you very much.
Thank you, Eric. That was a very interesting kind of a detective story there. I appreciate it. It's interesting. And I see there was one question in the chat, and I think it's pretty well been answered, but I'll ask it anyway because you showed some pictures of the cores. It was what's the diameter of those cores?
Those cores, they're about 1.75 inches in diameter, and when we collect them, I said the coring is done with hollow steel tubes. The lead tube, the first tube that we collect with, is actually milled, so we have a clear polycarbonate plastic liner that fits right inside it. And so when we hammer down the 5 feet and then pull it back out, then we unscrew that tip and we pull out this 5-foot long clear plastic tube that's filled with the sediment. And so that's how we get successive cores, and we're able to take them back to a lab and describe them in our own time.
I'm guessing you need to wear ear protection when you're doing that.
You very much do. Yes, it's steel on steel hammering for about 8 or 9 hours a day.
Yeah, I'm going to open the Q&A here from Joe. What effect did glacial rebound have on shifting river patterns?
That is a really good question, and for the longest time I didn't have a solid answer for it, because you would have had, during the glaciations, you would have had glacial isostatic depression, and then of course rebound once the glaciers are treated. But we more than the depression and the rebound, the thing that we'd actually have to worry about is what's called a glacial forebulge. And when you have glacial isostatic depression, you're pushing down the Earth's surface by the weight of the glacier, and underneath that you actually have to move mantle material to accommodate the Earth's surface being pushed down. And so down at depth in the Earth, that mantle material gets pushed out in front of the glacier, and so rather than having glacial depression, you actually have a glacial forebulge, they call it. The ground gets pushed upward out in front of the glacier, which would be a real deterrent to stream systems and the like, it would seem. I've got a colleague from your neck of the woods, a colleague at the University of Minnesota Department of Geoscience. His name is Andy Wickert, and he has done some really, really interesting work looking at the bedrock floor of the Mississippi River, and he's actually deduced that there is evidence in the shape of the bedrock floor of the Mississippi River for a spillover, just like I described in here, that actually cut across this glacial forebulge. So the effects of depression or a glacial forebulge were significant, but there's evidence that they were not so significant to have prevented this kind of activity happening.
Okay, thank you. A question from Peter. First of all, he says, wow, great talk. Then what is the wavelength of the LIDAR emissions?
Oh boy, you're hitting me with questions that I have no clue. I literally do not know. It's a laser that's being shot where they're doing a 2-ray travel time, but I have no clue what the wavelength is that they're using.
And a question from Rod. What are your thoughts on why no glaciers in that part of Wisconsin?
In the driftless area? Yeah, so that's a multi-part thing. The first is when we look at the you know, we'll talk about it in the let's go back to that pretty picture. We'll talk about it through the 3 glacial system that I talked about, pre-Illinoian, Illinoisan, and Wisconsin. So the pre-Illinoisan, the ice was coming out of the northwest. It was flowing out of the Canadian Prairie provinces, and it was flowing to the southeast across Minnesota and Iowa. And these glaciers, they when they're in their advanced phase, they advance until they get into a warm enough climate where melting, the rate of melting matches the rate of ice being transported into the area. That's when they reach a stable point. That can happen anywhere. It's a function of how much ice is being delivered and how warm the climate is. So that one was just sort of a random happenstance of that's how far to the south and east that the pre-Illinoisan deposits went. The Illinoisan deposits, and in fact, let's go back to that image. So I'm not just talking into empty space. We've got something to look at. There we go. Okay, so these are the ones that were flowing to the southeast, and this was just how far they were able to flow before melting matched ice influx. These Illinoisan deposits, these were coming out of the northeast, flowing to the southwest, and so we're not sure about why this was happening, and why what I'm going to explain here was happening. But what we do know is that the ice coming down the Lake Michigan lowland at that time was, you can see that it's more extensive. It extended farther down to the south across Illinois and Indiana. But if you get over here into where the Green Bay lowland is, there was very little evidence for ice. You know, we don't understand why that was happening. In fact, I've been doing quite a bit of research looking at it. You know, the end result is that for whatever reason, there was no Illinoisan ice in the Green Bay lowlands to come down and block this. And then the third part is the Wisconsin age ice. So ice was coming down the Green Bay lowland. It was coming down the Lake Michigan lowland. In both those cases, the ice was flowing parallel to these lowlands. You can see, you can sort of get the sense of it. But if you were up here, this ice that was up here in the Wisconsin, this was trying to cross the Lake Superior lowland. And the Lake Superior lowland it's a failed mid-continent rift. It's tremendously deep compared to Lake Michigan, for example. So, you know, of course, the deepest points in Lake Superior today are 1,500 feet deep. So that's a huge hole in the ground. And not only that, but that ice was trying to cross it perpendicularly. And so the Wisconsin ice that otherwise would have gotten all the way down here was held up by that deep hole of Lake Superior, and ice was able to get across it into northern Wisconsin, but not flow any farther south like it was able to in the Green Bay and Lake Michigan lowlands.
Okay, before the next question, Carol has a follow-up to one of the other questions. Google says airborne LiDAR uses 1064 nanometer diode pumped YAG lasers. So,
There we go. That is an answer that I would not have been able to get.
Okay, and then Patrick has a question in the chat. I remember reading once about a buried waterfall on a reverse Mississippi, I think in northern Iowa. Would
Yes.
that be part of an old stubby feeder to the Weiselung River, or not part of that system?
No,
Or maybe a figment of imagination.
in fact, that is the basis of Andy Wickert's paper that I referenced that indicated that the lake spilled over the glacial forebulge. So basically what he's documented is that if you trace the bedrock floor of the Mississippi River, not too far south of Dubuque, there is actually a place where the bedrock floor drops precipitously, something like 150 feet. I'm not sure if that's the number. It makes a significant drop. And then there's actually a section where the bedrock floor section just downstream from that, where the bedrock floor of the Mississippi River dips to the north. And so Andy documented that with borings that cut across the Mississippi River, so highway and train borings and the like. And that would have been at times when the Mississippi River was flowing without any sand and gravel in it, that would have been a waterfall right there on the Mississippi River. And the reason it's there is because the glacial lake Muscadet overspilled and cut that new narrow section of the Mississippi River across that forebulge, and then following the glaciation, when there was isostatic rebound off to the north, the forebulge collapsed. And so where it collapsed is where you've got that waterfall and divot today in the floor of the Mississippi River Valley, in the bedrock floor of the Mississippi River Valley. That was a paper that Andy had published in the journal Nature Geoscience in 2019, and I was a co-author on that with him.
Thank you. A question from Mark. I am interested in the Northwest Sands Long Ridge from Grantsburg to Bayfield. How could this form? Perhaps as a stream bed between two glaciers?
Yeah, I think you're referring to up in the Crex Meadows areas. Yeah, so you're talking about up here in this neck of the woods up here, I believe is what you're touching on. And that is that's part of the much more recent glacial story. So that has to do with spillover from some of the big glacial lakes that existed up along the ice margin back during deglaciation. So as ice was backing out of northern Wisconsin, backing out of Minnesota, backing across the prairie provinces, there were numerous big glacial lakes that were formed. So there was one in what today is the Lake Superior Basin. It was higher than Lake Superior. It's called Glacial Lake Duluth. And then stretching across enormous parts of the prairie provinces of Canada was Glacial Lake Agassiz. And at times when those began to drain, they began to drain with great outburst floods that would come down some of these pathways. And that stretch there in northwestern Wisconsin is one area that these enormous glacial outburst floods coming from Glacial Lake Agassiz down through Glacial Lake Duluth and then down that pathway into the Mississippi River, more routed. And so that's what those relate to.
Okay, let's see. Oh, yes, from Peter. Maybe I'm way off base here, but I thought southeast Minnesota was a driftless area. But based on the map that you showed, it was covered by pre-Illinoisan glaciation.
Yeah,
now considered driftless.
Let's go to this map. Yeah, so there's about, I don't know, 1,000 different definitions for the driftless area that people tend to use. We as geologists pretty strictly adhere to the definition of the driftless area as being that portion of the Midwest that was never covered by glacial ice. Different people define it differently for different purposes, not necessarily adhering to that glacial geologic definition of it. And one of the most prominent ones that you'll see is Trout Unlimited uses their own definition for the driftless area that does include tremendous areas in southeast Minnesota and northeast Iowa. And those areas were actually glaciated. So to a glacial geologist, we wouldn't call them part of the driftless area. Trout Unlimited does. They do it for a very legitimate reason. And their reason is that these areas of Minnesota and Iowa were covered by these pre-Illinois glaciations. So we're talking 1 million years maybe since the last time ice was there. And so much time has passed that most of the glacial sediment has been eroded away. And the stream pattern, that dendritic stream pattern, has been reestablished across the parts of these areas. And importantly to Trout Unlimited, because you've got those stream patterns reestablished, you've got the cold springs that feed into them, so you've got great trout habitat. So they lump it all in what they call as the driftless area that does include huge chunks of Minnesota and Iowa. Like I said, geologically, we would not say that it is. Geologic mapping in those areas of Minnesota and Iowa have definitely identified glacial deposits indicating that they've been glaciated. And towards that end, we are in the final stages of publication of a 2-page publication from our office that defines the driftless area on a map based on the glacial geologic history. So this is not I am the lead author on it. I'm not the only one who worked on it. In fact, I very intentionally had geologists from the Minnesota Geological Survey, the Iowa Geological Survey, and the Illinois State Geological Survey. So the 4 state geological surveys got together, and this is our publication that is defining the driftless area based on the extent of glacial deposits. And it's a much more refined map than what you see on the screen now, but that is what we're seeing. The areas in Minnesota and Iowa in this publication, we refer to them as driftless style topography because they do have a topography that's similar to the driftless area, but they are not driftless. They were glaciated in the past.
How soon do you think that'll be coming out?
If I hadn't been so busy today, I would have been doing the final comments that need done based on the peer review that it went through. So probably by summertime it'll be out. You know, when it comes out, I'll be sending an email to plenty of folks, and I'll be happy to send it to the moderators here who invited me to come to the talk so y'all can get a peek at it. It's a 2-page, 1-page front and back kind of thing. We call it a fact sheet or an educational series pamphlet, but it does have some gorgeous maps that show the driftless area. And in fact, it's got one of the 2 maps is a very similar, very close version of this. The other one is just a gorgeous map showing the driftless area.
Great. Yeah, please do send us that email, and then I can let the rest of our membership know about it.
Sure thing.
And if anybody else has questions, enter them now, because I'm down to the last one from Carol. Can you speculate on what ancient formation made this a driftless area?
What ancient formation?
Yeah, I think why did the glaciers not go there? I think that's basically what the question is.
Yeah, so I mean, this is the, especially this is the thing about the Wisconsin glaciations, those most recent ones. They would have wiped the driftless area off the map, except that ice coming down from the northeast got blocked by the Lake Superior Basin. Ice can flow uphill because it flows based on pressure, not gravity. But trying to flow uphill out of a 1,500-foot hole in the ground was too much of a task to expect that ice to be able to flow as far south as it did when it was coming out of the Green Bay lowland, out of the Michigan lowland, or just flowing across southern Minnesota and into Iowa.
So you could say we were in the ice shadow, or it was in the ice shadow of Lake Superior.
It absolutely was. That is the best way to put it that I've ever heard, I believe.
Okay, that's the end of the question. Steve, I don't know, do you want to talk about 2 weeks from now anymore? You mentioned it earlier.
Well, I will stop sharing.
No, we'll be back at the University of Minnesota with